Okay, in this video we're going to look at deriving the big three kinematics equations for constant acceleration. So what we've been looking at primarily are using graphs and using the graphs of motion to analyze different aspects of motion. For example, using the acceleration graph to find the change in velocity, or using the velocity graph to find the displacement, or using the slope of velocity to find the acceleration. But what we want to do is look at this very specific case of when things are at constant acceleration and see if we can use those graphs to deduce some general expressions, some general formulas from there that will work as a set of tools that allow us to make predictions and solve problems analyzing the motion of objects without having to go through the process of graphical analysis. So we're going to come up with some general expressions using this specific case. So let's take my Ford Pinto. Let's say my Pinto is putzing along at a constant acceleration, and we were to plot that. That constant acceleration would look like a flat line, like so. And let's say we just took a time interval from time 1 to time 2 and found the area. Well, based on what we've learned previously, we know that the area of this curve would be the acceleration, since it's constant, it's not changing, whatever a is, times delta t. And that would tell us the change in velocity of the object from time 1 to time 2. Now, to keep things a little simpler, we're going to use the equivalence of t for delta t in these equations. So whenever you see time interval, we're talking about time elapsed, or t, we're going to use that. So acceleration times time is change in v. Well, change in v really just means if I have some final velocity minus some initial, whatever that changes is whatever I end up at minus whatever I started at. So we are going to substitute that in as well. So whatever velocity I'm currently moving at minus the initial is equal to the rate of acceleration that I'm accelerating at times the amount of time over which I accelerate. So if we add v naught to both sides, we get my final velocity is equal to my initial velocity plus my acceleration times the amount of time that goes by. And that is based off of this idea that the constant acceleration area is a times t, and that's my delta v, which is v minus v naught. Talking too fast. So this is our first kinematics equation. Okay, another thing I'm going to write off to the side, which we're going to use later, v minus v naught is equal to a t. So we're going to keep that in mind for the second scenario. And that is, what if we were to take this constant acceleration motion and plot it on a velocity time graph? So let's say my time t1 is here, my time t2 is here, and if this is a constant positive acceleration, I'm going to have an increasing constant slope line where this is my initial velocity, whatever that value is, and whatever this value is my final velocity, v. And the other thing I can know from a velocity time graph, besides finding the slope to find a, is that the area underneath this curve, which I'm going to break into both a rectangle and a triangle, the area gives me the displacement of the object during that period of time. We derived that in a previous video. So let's come up with a general expression for the area under a VT curve for constant acceleration. Remember, this A is the slope of this line. Okay, so there's a connection here. If it wasn't constant acceleration, you would not see a straight line slope. It would be a curve of some sort. And so the simple geometry I'm going to show you wouldn't work. So this only works for a specific case of constant acceleration, the algebra here. All right, well, I know that this is my initial velocity, this is my final. And this t1 to t2 is my delta t, or t as we're calling it. We're just simplifying it. So if I want to find the area of this rectangle, the base is the delta t or t, and the height is v naught. So this area is v naught times t. So let's start with delta x. the first part from triangle 1 is v naught times t. It's the easier one. And I'm going to add to that then the area of this triangle. Well, this area, since it's a triangle, it's 1/2 base times height. Well, my base is going to be the length of this segment, which is also t. And then my height from here to here is going to be my difference between v and v naught. So 1/2 t times v minus v naught. So if I were to find v naught times t and find 1/2 times t times v minus v naught and add those together, I would get the displacement of the object from time t1 to time t2. That's another expression I can derive. Now, I want to simplify this a little bit more to get rid of this v minus v naught. This is going to make the terms a little bit messy, so I want to get a into this equation to simplify this final term. Well, this is where I go back to my initial equation. I know that another way I can write v equals v naught plus at is by subtracting v naught back to the side. The difference in velocity, or delta v, is just the acceleration times the time. So I'm going to substitute in at for my v minus v naught. So delta x equals v naught t, which is my first rectangle, plus now 1/2 t times at. Now if you notice, I have t times t, so I can substitute this further as v naught t plus 1/2 at squared. So in this case now, if I know the acceleration of an object, I know the amount of time it accelerates, and I know its initial velocity, I can solve for the displacement. Furthermore, if I know the displacement, initial velocity, and time, I could substitute and do some algebraic manipulation to solve for a. So it gives us an algebraic expression that we can make predictions for an object moving at constant acceleration. Notice, what is happens if my acceleration is 0? This term goes away. I'm left with delta x is v naught times t. Looks familiar, right? Because v equals delta x over delta t. For constant velocity, where this is the same, right? I multiply by delta t. Delta x is v times t. V times t. So really, this works for an acceleration of 0 because this term goes away. All right, so that's equation number 2. Okay, for the third one, I'm going to eliminate time from the equation. So this one gets a little bit messy in terms of the algebra. I'm looking for my blue pen. Can't find the blue. Let's go red. Okay, I want to eliminate time. So I have two equations. V equals v naught plus at, and delta x equals v naught t plus 1/2 at squared. If I use substitution and eliminate t, I get a third expression, which I'll do on this second page. Let me clean this up a little bit. Okay, so v equals v naught plus at. I'm going to subtract v naught, v minus v naught is at, and I'm going to divide by a to get an expression for t. V minus v naught over a. I'm then going to go back to my second equation. Delta x is v naught t plus 1/2 at squared, and I'm going to substitute in for t, and then I'm going to simplify. This will get a little messy, so bear with me. All right. Hopefully the algebra gods are with me and I don't make any mistakes on this one. Delta x equals v naught times v minus v naught over a plus 1/2 a times v minus v naught over a squared. So let's simplify. Delta x equals, so I have v naught times v over a minus v naught squared over a, so I'm multiplying that out, plus 1/2 times a. Now let's multiply this term out first. Do brackets. So I have a v squared minus v naught times v plus v naught squared over a squared. Okay, so if I multiply this out, I think I'm going to get some terms to begin to cancel for me. So delta x is v naught times v over a minus v naught squared over a plus 1/2 a, and let's just do this, v squared over a squared minus v naught v over a squared plus v naught squared over a squared. Multiply that by a, so all these a squareds go away. Actually could have done that in the previous step, don't know why I waited. And then let's multiply through the 1/2, so I end up with v naught v over a minus v naught squared over a plus 1/2, or let's just do v squared over 2a minus v naught v over 2a plus v naught squared over 2a. Kind of a mess. Delta x. Alright, what can cancel here? So we have a lot of v naught squareds and v squareds. So let's get these grouped. So v naught times v over a minus, oh, I forgot something up here. This should be a 2. Oops. 2. Because this cancels. These terms cancel out. Because I would have a v naught times v minus a v naught times v, so it would be 2 v naught v. And I'm left with delta x equals a minus v naught squared over a plus v naught squared over 2a. So that's a 1/2, so I'm left with a minus v naught squared over 2a. And then I have a plus v squared over 2a. I'm starting to get somewhere now. So let's flip these and combine. Delta x equals v squared minus v naught squared over 2a multiplied by 2a multiplied by 2a. Getting somewhere. V squared minus v naught squared equals 2a delta x. I'm going to swing this over so I get my final expression. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Oops, I got so far I ran off the paper. And that is equation number 3. Now, don't freak out. I won't make you replicate that on a test. Don't need to memorize that. Don't even need to know how to do that. There's a lot of algebra there. Hopefully you can follow my steps. If you're not sure what I did somewhere, feel free to ask me in class if you want to know. But know that this is my third equation that works for constant acceleration. So, to review, okay, important fact. These big 3 equations work for scenarios of constant acceleration only. An acceleration of 0 works as well. When the a varies, we got to use more advanced techniques. Hint, it's calculus. You'll get there. For now, we're looking at the algebraic form. And these are our big 3 in the form that we're going to use them. Velocity equals initial velocity plus acceleration times time. Displacement, delta x, is equal to initial velocity times time plus 1/2 acceleration time squared. Note it's just the time squared in that. And then final velocity squared equals initial velocity squared plus 2 times a times delta x. And there are your big 3 kinematics equations. Now we're going to have lots of fun using those to solve problems and make predictions.